All right, we're doing part 2, problem 3, practicing finding an empirical formula from lab data. This one talks about ethyl butyrate, and ethyl butyrate helps pineapple smell like pineapple. How cool. It contains only carbon, hydrogen, and oxygen, and somebody went into the lab, analyzed a sample, and found exactly that much carbon, that much hydrogen, that much oxygen. They must have used some really, really good machines to get to that many digits of precision. But that is certainly something you could find in a really good industrial chemical laboratory. So, before starting the broadcast, I did the tedious but really important work of turning each of those numbers of grams into a number of moles of carbon, hydrogen, and oxygen. As a side note, if you used a periodic table with more digits, you might get more sig figs. And maybe I preserved a few too many sig figs here in my zeal to show how good this equipment is. Anyway, because we're finding an empirical formula, which is going to be a simple whole number ratio, we don't need as many sig figs, but it's fun to have them. I wanted to remind you, by getting to this far and then pausing, that the important idea here is that you have some number of oxygen particles expressed in moles, some number of hydrogens expressed in moles, some number of carbons expressed in moles, and if you want to find simple whole number ratios, the key is going to be to divide each of these by the smallest one. Who's smallest? Oh, it's the number of moles of oxygen that's smallest. So I'm going to divide each of these three numbers by the number of moles of oxygen. I'm going to type them all into my calculator, and my calculator told me that it was about 2.997 moles of carbon, 5.99 approximately moles of hydrogen, and of course, if this number is divided by itself, 1 mole of oxygen. So I feel really confident that it wasn't anything other than 3, 6, and 1. And so I'm going to say that the empirical formula is C3H6O. You don't have to list them in this order in 10th grade. It's a convention that organic chemists use to write them in that order. I went ahead and cheated and used Google to look up what ethyl butyrate is. The molecular formula is... So that's cool. It's a nice reminder that the molecular formula can reduce sometimes to a smaller empirical formula, and that a reminder that the empirical formula is just the simplest whole number ratio between them. And analyzing real data in the lab won't tell you whether it's this compound or this one or still another one from just this analysis. You'd have to do other analysis. You can be done right now, but also I'm going to point out one more little fact about why I used singleton atoms even for hydrogen and oxygen. If you find oxygen in nature or hydrogen in nature, you're going to find H2 and O2, but because somebody broke it down in a lab and found there were that many grams of hydrogen, I want to know how many moles of hydrogen were part of this compound, not how many moles of H2 gas are going to get released if I combust it, or if I, in some other way, extract the H2. If I combust it, it'll probably come out as H2O. Likewise here, we're not actually producing oxygen gas. We're finding that there's that many grams of oxygen, so I just want to know how many moles of oxygen atoms there are, even though the number of moles of oxygen gas, if that's how it came out, might be different from this. So that's why I didn't double any of these. I think you could probably get the same answer if you said a mole of H2 and grams of H2. I think the conceptual confusion would sort itself out in the math, but in principle, it's smart to just look at isolated atoms when you're trying to turn empirical data into an empirical formula.